will see and come.
Okay. Then
We
from
think
next module,
more understandable.
Yes,
That
ma'am.
will
We'll
be.
Ma'am,
understand
we can
more.
follow you when you will teach us.
Yes, ma'am. Ma'am, because these are totally new to us. So,
okay.
ma'am, sometimes it gets difficult
Okay.
to
So
follow.
I will complete this module today. So after the class, I will send this to you, module 5. Okay. And from next module onwards, I will send the PPT. If you want
Thank you,
that,
ma'am.
do that. If
Thank
you
you,
start
ma'am.
with that
Thank
particular
you, ma'am.
module, send the
Ma'am, then it will be very
image.
easier to
No
follow.
problem. No problem. But because of these, your attendance should not be decreased in the class.
No, ma'am.
No, ma'am, we still have to understand from you.
Okay.
And we will have internal after vacation, means
Yes.
holiday.
Yes. Yes.
Means which type? Written type or Viva?
For theory subject, definitely a
Yes, yes,
written
ma'am.
examination. Definitely a written
Okay,
examination will be there
okay,
when college will reopen after the
okay, ma'am.
vacation. Okay, let's start with three-phase inverter. So, do you have any question from single-phase inverter, voltage source inverter, half bridge type, full bridge type? These are basic configuration of single-phase voltage source inverters. Okay, so this is the circuit diagram of basic three-phase voltage source inverter. So inverter means the DC to AC converter. Inverter helps us to convert the DC supply, the fixed DC supply, into uh, variable frequency, variable voltage AC supply. So any AC machine drives can be the load that can be connected across the load side of the inverter circuit. So in this diagram, capital A, B, C are the three phases or the output AC lines that you need to connect with any three-phase load. It may be a resistive load, maybe RL type load. So here load circuit has not drawn. Okay, so you can see EDC is the DC input. The battery cell can be the source here at the input side of this inverter. Other than this battery source, also we can use rectifier unit. Rectifier also uh, produces DC output from AC. So here I have taken the fixed DC, the stiff DC voltage source across the input side in parallel with a capacitor. So this is the capacitor. You can see whose initial voltage must be equal to the input DC bus voltage, which is EDC here. It is present here to eliminate the ripple present in the DC input voltage. Now here in three-phase configuration, three limbs are required. Three limbs or three legs. Each leg will be having two number of semiconductor switches. So in this diagram, these are IGBTs, insulated gate bipolar transistors. These are all IGBTs. So total three limbs are there. So total 6 number of switches are required to connect in this type of configuration. Okay. And here load is basically three-phase balance type load. You can see here the star type load circuit has drawn. These are all impedances of the load, and these terminal A will be connected with this center point A between the two switches present in the first limb. This B will be connected with this terminal, which is also the center point of the second limb between the two switches SW3 and SW6, and this C terminal will be connected here, right? So if you connect these three terminals with these three center points, then the load circuit will be connected with this inverter circuit. And here I have taken a star connected load. The load may be of delta connected also. Now, what is the working principle? How these switches will operate? So each switch has one gate terminal other than the emitter and collector. Right? This is the emitter, this is the collector, and this is the gate. So in order to operate, in order to turn on the switch, you need to provide a suitable gate signal at the gate terminal, right? So gate signal will be coming from the control circuit or control strategy that I have explained earlier for single phase configuration. So control circuit can be of two types. One is using modulating signal, which is a 50 Hertz sine wave, or it can be a constant DC voltage, as shown in the second diagram. So if you compare the sinusoidal signal with a high frequency carrier signal, this type of pulse signal will be generated, which you can provide with the gate terminal of the switch. Here only a half bridge topology has been shown in this slide, having only two number of switches. Right now, if you add two more limbs, right, it will be a three-phase configuration. It will be a three-phase inverter circuit. So definitely for three-phase configurations, we need another two comparators to compare two more sinusoidal voltages as modulating signals along with the same carrier signal at high switching frequency. And here these three sinusoidal voltages for three different limbs must be 120-degree displaced by each other for balanced load, right? So if the reference one for first limb is expressed as Vm sin omega t, then definitely the reference signal for the second limb will be Vm sin omega t minus 120, and for the third limb it will be Vm sin omega t minus 240 degree, right? So three different sinusoidal voltage signals will be used as the modulating signals for the control circuit, which will be compared with a carrier signal, a common carrier signal, which is a triangular signal with high switching frequency. Okay, now if we compare three different control pulses, the gating pulses will be generated, and those gating signals will be supplied to these gate signals to the top switches of the three links, right? They are marked as 1, 3, 5. The top switches present in the three-phase inverter topology will be always marked by these numbers 1, 3, 5. Follow the sequence always. Whereas the lower switches will be marked as 4, 6, 2. Because based on these markings, the suitable gate signals will be designed. If you change the sequence, definitely you need to change the control circuit also. Okay, so whatever pulses will be fed to the top switch of each limb, the complement of that signal should be fed to the bottom switch of the same limb. Okay, because no two switches from one limb should operate simultaneously. When one is working, so when upper one is working, definitely the lower one must be turned off, right? Now suppose, for example, the switch SW1 is working. Switch 1 is made turn on. So what will happen? The current will be passing through this switch, right? So whenever the current is passing through this switch, what will happen? The current will flow through this switch. Then since this A terminal is connected with this load, it will be sent to this load, and then it will try to return back to this negative supply, either any of these four switches. right? Is it okay? Because this will turn off. Whenever SW1 is working, definitely SW4 will be turned off, because these two switches cannot be turned on simultaneously, otherwise this input side will be short circuited, so there will be no voltage across the output. So definitely the SW4 is turned off whenever SW1 is working. Okay, so the current needs a path to get back to the negative supply, negative DC voltage. Okay, and what are the possible directions, possible way?
Ma'am, A and C.
Let me join the terminals first, the load terminals first. The current is coming from this DC voltage source to this switch SW, then it will be sent to the load connected with this terminal A, this side, then it will come to this node. This N is nothing but the neutral point. It's a star connected load, so all three load must be connected to a common node. That is the neutral point. So now the current can send back to the negative DC supply either through this or through this. Right? So it's a three-phase system. So definitely when SW1 is working, the current should flow through this to return back to this B phase, and through this to return back to this C phase. Okay, because the current cannot flow through these two switches, because if the current flows through these SW3 or SW5, what will happen? It will again send back to the positive DC supply. So these two paths are not uh, the correct directions, right?
Ma'am, but it can reverse diode also. Oh no, sorry.
This you are talking about these two. You are
Yes, ma'am, I
talking
was talking about that too only.
no, no. These two diodes should not be conducted. See, these two are not working because you will not send any gate signals to these gate terminals at that moment when this one is working, because theoretically no current should flow through these paths, because again it will converge to the starting point, which is the positive DC. So again input side will be shorted. And SW4 also cannot be operated whenever SW1 is working. So definitely these two switches must be conducting in order to provide the two return path of this current, one through phase B and one through phase C. Okay. What is VA0, VB0, VC0? These are basically phase voltages. Phase voltages, okay? So switch 1, SW1 is working for 180 degree. This is 60, 60, 60. So total is 180 degree. And when switch 1 is working, definitely switch 4 will not be working. So switch 4 will be working from 180 degree to 360 degree. Because initially we have chosen a 50 hertz AC signal. Fine. Now phase voltage VBO. Phase voltage VBO means here three balanced load has been taken. So phase voltage VBO must be 120 displaced by phase 1. See, this is 120 to pi by 3. So it is conducting. I mean, whatever switches are under this phase V will be conducting for 180 degree. And this VBO, the phase voltage for phase B, is deviated by 120 by phase A. And similarly, VCO, the third phase voltage for phase C, is displaced by 240 from phase 1 and 120 from phase 2. Now, these three are balanced three-phase voltages. So these are not phase voltage waveforms. Phase voltages are definitely sinusoidal one, right? So I have drawn this waveform to make you understand that SW1 will be working for 180 degree and SW4 will not be working when SW1 is under operation, right? So just after 120 degree from SW1, SW3 will be under conduction, and after 120 degree SW5 will be under conduction because 1, 3, 5, these are the top switches of this inverter topology, right? So after starting point of SW1, SW3 will start its conduction because it is under phase B, but the phase difference between these two should be 120. Again, after conduction of SW3, who will conduct next? SW5 because it is under phase C, but it should be under conduction after 120 degree conduction of SW3 or 240 degree conduction of SW1. And look at the responses. When SW5 is working, SW2 is not working because SW2 is the complement of SW5. SW6 is the complement of SW3. So SW6 will not be working when SW3 is under operation. Right? And here basically we are joining three single phase half bridge configurations. Look at the circuit diagram of half bridge single phase inverter. Here only two switches are working, connected across a DC source. So here, if you connect two more leads, what you will get? You will get the three-phase inverter circuit. So basically, here in three-phase topology, half-bridge configuration is there. That means the magnitude of the voltages is just half of the input DC voltage that we have already obtained from half-bridge configuration. Here, across each switch, only half of the DC input voltage will be impressed. So here also we'll get 0.5 VDC as the peak voltage for each switches. Now this VAB is the line voltage. Line voltage means the voltage between these two lines or these two or these two. And this waveform, this green colored waveform is VAN, that means the phase voltage waveform. Phase voltage waveform between this phase A and this neutral, VAN. Phase to neutral voltage or phase voltage waveform of a three-phase inverter when each switch is conducting for 180 degree. That's why this mode is known as 180-degree conduction mode, where each switch is working for 180 degree. Now, have you understood this thing?
Yes, ma'am.
Yes, ma'am.
Understood. Yes, this is the suitable schematic diagram of a three-phase VSI. You can see this is the voltage source, this is the source current, capacitor in parallel with the voltage source. These are all switches, 6 switches, like this one. Here IGBTs are taken, but here these are all the symbol of semiconductor switches, right? So S1, S3, S5, the top switches, and S4, S6, S2 are the bottom switches for 3 phases respectively. This is phase A. This is phase B, and this is phase C. And this is the star connected 3-phase load, right? So whenever S1 is closed, that means whenever S1 is conducting, what will happen? Current IS will start flowing from positive DC to this switch, then it will come here at this junction, will next come to the load, and again it will try to return back to the negative supply either through this X6 or through this S2 via phase B and phase C respectively. That means whenever switch 1 is working, switch 6 and 2 must be working together to provide the path for the current to flow from positive DC to negative DC. And make sure S4 is totally turned off, and S3 and S5 should be turned off also, because they are under phase B and phase C, under positive phase B and positive phase C, because they are connected. They are used here as the top switches in this topology. Top switches means they are connected with the positive phase B and positive phase C respectively. Okay. That means if I draw a timing diagram, what I should get from the timing diagram. So this is pi means 180 degree, right? So this is for switch S1. This is for switch S1. So switch S1 will operate from 0 to pi, right? Now switch 3, okay, look at switch 5, switch 6 and switch 2, because they will be working together when this W1 is turned on. So look at this. This is also a timing diagram. Can you follow this diagram? This is SW6. So SW6 is under operation for this time duration 0 to 120 degree or 0 to 2 pi by 3 because SW3 is not working. S3 and S6, these are complement switches. So S3 is not conducting. S3 will start its conduction just after 120 degree from SW1. Right? So S3 will start its conduction at this moment at 120 degree. That means the complement switch of S3, which is S6, is working for this period because it's a voltage source inverter, means only square wave pulses will be sent to the switches. As shown in this diagram, only square pulses are required to send to the gate terminals. And look at the time period for which SW2 is working. See, for this duration, SW5 is working, starting from this position, or from 0 to this 60. This is 60. And each switch will conduct for 180 degree, right? So the complement of S5 is S2. So SW2 is working for this period, right? That means definitely when SW1 is working for a particular time period, SW6 is working, and for another particular time period, SW2 is working. And this period, 60 degree to 120 degree, all three are working simultaneously. 1, 6, 2. Right? For 0 to 60, 1 and 6 are working along with 5. What is 5? This one is 5. And for 120 to 180, 1, 3, and 2. These are working. 1, 3, and 2. These are working because at this point, at 120 degree, switch 3 has started its conduction. That means there is a changeover of phase from phase 1 to phase B. Okay? Since it's a star connected 3-phase balanced load. So exactly at 120 degrees, switch 3 will start its conduction. So whenever switch 3 will be working, what will happen? Switch 6 should not be turned on. You see, look at the timing diagram. SW6 is automatically turned off at this moment. Omega t equals to 120 degree. So as soon as SW6 is turned off, what will happen? Current requires another path to return back to the negative supply. So simultaneously, who will start its conduction? SW2. SW2. Okay. So in this way, all 6 switches are
Ma'am, so
loaded.
why in first segment SW5 switched on for a time being 0? This one, yeah.
This time period. Okay, for this time period, look at the timing diagram. 4 is not working because SW1 is working, right? 3 will be under operation exactly at this 120, and 5 will be exactly after 240 from the first one. So this is 180. 180 plus 60 means this is 240. So if this is 240 and this is 60, because 5 and 2 are complement to each other, right? That means
Yes, ma'am, yes.
for this last 180, S2 must be under operation. So 60, 60, 60, 180. That means before SW2, definitely somewhere between the 0 and 60 degree, S5 was under conduction. That means for this small interval, 0 to 60 degree, only 1, 6, and 5 were working. 1, 6, and 5 are working. Follow this circuit, then you'll be able to understand clearly. But only 0 to 60 degree current is passing through this switch 1, load. 6 is working, and through phase C, 5 will be working. Okay.
Okay, ma'am. Okay.
Just a minute. If I can draw it, then it will be easier for you. Because star connected load is connected here. Just wait. These are 3 links. So S1, S3, S5, the top switches respectively, and S4, S6, and S2 respectively. And this is the DC input. Input DC bus capacitor. This is C, this is VDC. Okay. So how to connect the load? This is for phase A, this terminal, the center point. This is for phase B, and this is for phase C. Okay. So what I will do, taking only the resistive load, pure resistive load. This is the neutral point, right? This is for phase A, RA. This is for phase B, say RB, and this is for phase C, RC. This is the load, the 3-phase load, which is a star connected load. So it has a common point, the neutral point, marked as capital A over here, right? So whenever switch 1 is working, current, this switch will be closed, current will be flowing like this, right? Now again, the current can flow through this RB and RC following the path S6 and S5 for the first 60-degree interval, because for the first 60-degree S1 is working, right? And as per the timing diagram, what we can get, that S5 is also working. S5 is also working. Why? Why? Because S5 will, since S5 is under phase C, so phase C is 240-degree displaced by phase 1, right? So this is omega t equals to 240. That means for the last 180, SW2 is working. That means before that, that means this small interval 0 to 60, S5 is working. That means current is also flowing through this switch for that small period, this source current IS, because both these two switches are now closed for that small interval, the first 60-degree interval. Am I clear to everyone? That means current is flowing through this. So this should be opened because it's a complement of SW1, like this, that is coming to this neutral point. And also current is flowing through this switch because this switch is 5 is also forward biased because current is now flowing. So this should be turned on. So current is flowing through this switch. So this is closed for this. So definitely current will flow to this resistance RC till neutral point. Okay. And these two positive currents through these two switches which are under positive supply will be returned back to the negative supply only via S6. So whenever these two from top switch S1 and S5 are working, one from bottom which S6 must be turned on because S4 cannot be turned on because it's complement of S1, and S2 should not be turned on because it is complement of S5. Okay. Now is it clear to everyone?
Yes, ma'am.
Okay. And following this same principle, the other switches are also working. And thus we obtain this type of stepped voltage across each phase like VAN, VBN, and this type of waveform, this type of voltage signal across each line to line. VAB is the line to line voltage, VAN is the phase voltage. Okay, so this is at 1/3 EDC, and this is at 2/3. This peak is at 2/3 of EDC. So mathematically we can prove why it is 1/3 of EDC or why it is 2/3 of EDC. For that you have to draw the equivalent circuit for each 60-degree interval. Now, any doubts or any queries from this three-phase inverter? Okay. So next is PWM, the sine pulse width modulation technique. Sine pulse width modulation technique is one type of PWM technique where the modulating signal is a sinusoidal signal. The PWM strategy means the comparison between a modulating signal with the triangular or high frequency carrier signal as shown in this slide. So this pink colored waveform is a triangular one, which is a carrier signal at very, very high frequency, right? And this blue colored or green colored signals are the modulating signals. Here, these are sinusoidal signals because this is a sinusoidal pulse width modulation technique or SPWM technique, the widely used techniques in all types of power electronics converters nowadays. So in sine PWM inverter, the widths of the pole voltage means what? The voltage difference between this center point and the common point of this input. So that's why we need to have this type of neutral point or common point across the input so that we can calculate, we can measure the pole voltage, because pole voltage means the voltage difference between each pole, that means the center point between the two switches in one link with respect to this common point, neutral point. That is called the pole voltage, right? So in sine PWM inverter, the widths of the pole voltage pulses over the output cycle vary in a sinusoidal manner. So suppose in this diagram I have chosen two sine waves. So blue one is the modulating signal for pole A, right? That means for phase A, and green one is the modulating signal for phase B. So since this type of control strategy I have taken here for two phases only, that means here definitely phase B is 180 out of phase with phase A. So this is the case for a two-phase system, not the three-phase, two-phase system, where phase B is 180 out of phase with phase A. That's why I have chosen Vm sine omega t for the first phase as the modulating signal, and minus Vm sine omega t, or you can say Vm cos omega t, not minus Vm sine omega t, Vm cos omega t. Vm cos omega t for phase B. And the green one is just 180 out of phase with phase 1. When blue one is at positive maximum voltage, green one is at negative maximum voltage. That means they are 180 degree out of phase by each other. Okay, so these two are modulating signals, one for phase A, one for phase B, which are being compared with a high frequency triangular signal to provide this type of pulse signal. So blue one will be generated when the pink one and blue one here in this case are getting compared, and this type of pulses will be obtained when these modulating signal, the green one, is being compared with this pink color waveform. Okay, and third, the last graph is showing the line voltage graph. Line voltage graph. This is VAO, that means for phase A, between phase A and the neutral point O, and this one, the third one is for phase B, between the phase B and the neutral voltage VBO, the phase voltage. Right? So PAB, the line to line between the two lines A and B, which is definitely VA minus VB. Okay, so combining these two, second and third waveforms, you will get the fourth one. See, this is not a pure sine wave. This is the output. VAB, this is the output. If you connect a load between phase A and phase B, you will get this type of load voltage waveform. Right? And it is following the sine PWM pattern. It's not a pure sine wave. It's called a PWM based sinusoidal signal. Because here applying pulse width modulation technique, by applying sine pulse width modulation technique, we are getting this type of sinusoidal PWM sinusoidal AC signal at the output of inverter circuit. Okay, it's a two-phase system. That's why look at the heading. It's for single-phase half-bridge inverter. Single-phase means it's having only two phases. Okay, so the major advantage of this technique, this PWM technique, is to eliminate the harmonic components, because this type of PWM based sinusoidal signal contains less harmonics. Only the lower order, lower frequency harmonics are present. Lower switching frequency harmonics can be eliminated by connecting a small sized filter across the inverter circuit. But all the higher frequency components can be eliminated by using this type of PWM strategy. That's why this one is the most suitable technique in any power electronics inverter circuit. Any question up to this?
Ma'am,
Yes, Kurushika.
ma'am, I checked the Google Classroom. You have sent till module 2 AC. After that, you didn't send.
Module 1?
Module 1 and 2 you have sent, but after the modules 3, 4, you haven't sent.
3 I haven't started yet. After 1 and 2, I have
You
started with
started 5.
module 5. Yes. So I'll
Oh.
send module 5 by
Oh.
today.
Okay,
Next.
okay, ma'am.
Okay, next I'll be starting probably module 6. So I'll send the required study material to you.
Yes, ma'am.
for-
Before starting the module,
for
if you could
studying of
send,
module 6.
then we could
Okay.
follow better.
After module 6, I'll start module 3 and 4. Because module 3 and 4 are totally separate thing from these basic electrical and electronics. Now, any question from module 5? Because tomorrow we'll solve numerical problems from module 2 AC and also module 5 power converters. So you should be ready with these 2 chapters for the next class, next tutorial class. Okay, rule 1.
Present, ma'am.
2,
Present, ma'am.
3,
Present, ma'am.
4,
Present, ma'am.
5,
Present, ma'am.
6,
Present, ma'am.
7,
Present, ma'am.
8,
Present, ma'am.
9. Shoham.
Yes, ma'am.
10. Pushpindu. 11,
Present, ma'am.
12,
Present, ma'am.
13,
Present, ma'am.
14,
Present, ma'am.
15,
Present, ma'am.
16,
Present, ma'am.
17,
Present, ma'am.
18,
Present, please, ma'am.
19,
Present, ma'am.
20,
Present, ma'am.
21,
Present, ma'am.
22,
Present, ma'am.
23,
Yes, ma'am.
24,
Present, ma'am.
25,
Present, ma'am.
26,
Present, ma'am.
27,
Present.
28,